Start the recording and share. Okay. So yesterday we were talking about lines. Let me find where we were. So we saw how to determine that two lines are equivalent. We would now want to see if we can determine whether two lines intersect. So that's this question, determine whether the following two lines intersect. So of course they're not equivalent because these vectors are just not parallel. So they're not the same line. But the question is, you have these two lines. Let's imagine that this is one of them in 3 dimensions, and here's another. They might intersect at some point, or they might just be farther away from each other and just never intersect. So that's the question that we are trying to determine. So if the two lines intersect, then there are going to be two values, T1 and T2. So different values for the different lines, which will set each component equal. So you're going to get that 1 plus T1 is equal to 3 plus T2, 4 plus T1 times 3. And so what you can do is you can set up these equations for your X value. You look at the first component, the 1 plus the T1 times 3. So 1 plus T1 times 3. And you want that to be equal to 3 plus 4 T2. So that would be this 3 plus 4 T2. And you can do the same for the Y dimension, and you can do the same for the Z dimension. And now you have 3 equations and 2 unknowns, and you can use 2 of these equations to solve for the 2 unknowns, because 2 equations can solve for 2 unknowns. And then you can use the third equation to determine whether you intersect, because you would find the T1 and the T2 that you're looking for, and you will plug them into the third equation and see if you get an equality. So in order to solve for T1 and T2, what you can do is you can just take this 3T1, subtract it from this 3T1. So you end up getting 1. Okay, 1 is going to be equal, and then you subtract the other side of the equations. So you're going to get 6. So this is going to be this minus that. So 1 is equal to 6T2. And then this 3 subtracts from that 6 minus 3. So now you can solve for your T2. And you move the 3 to the other side. You get 4. You divide by 6. So you get T2 is going to be equal to 2 over 3, or 4 over 6. So now we found our T2. We can plug it in to our first equation, or to the second equation. And what you are going to get is that T1, so that would be, you have this 3T1, so you get T1 is going to be equal to 6 minus 2 times 3 over 2. Oh, what's going on? 1 second. Yeah, minus 2 times 2 over 3. So that's where you plug in your T2. And you divide all this by 3. Okay, and they tell us that that is going to give us 14 over 9. So you found our T1. We know what our T2 is. We plug all this into the third equation. So for the T2, you put in 14/9 in the third equation. So that's 5 times 14/9 right over here. And then for the T2, you put in 2/3. And these are not equal, so these lines don't intersect. Any questions? Yeah. Sure. Let me see.
Wait, how did you solve for T2 again?
You plug in the T1 into the second equation. So we got what T1 was right over here, or they have it. Sorry, what?
Wait, what did you solve for first, T1 or T2?
So you first solve for T1. And you do that by subtracting. So you have two equations. So let me write this somewhere else. 1 plus 3T1. 1 plus 3T1. So this is your first equation, is equal to 3 plus 4T2 is equal to 3 plus 4T2. So let's call this equation 1. The second equation gives us 3T1. So 3T1 is equal to 6 minus 2T2. 6 minus 2T2. This is the second equation. So the first step is to take the first equation and then subtract the second equation. So equation 1 minus equation 2. And that will give us, so from the left-hand side, you're going to get 1 plus 3T1 minus 3T1. And that's, of course, going to give you 1 is equal. And then the right-hand side, you're going to get 3 plus 4T2 minus 6 minus 2T2, which gives you -3. And so it gives you 1 is equal to -3, and then minus minus, so plus 6T2. So now you move the 3 to the other side, so you get 4/6 is equal to T2. Now, once you solve T2, you plug it into, let's say, the second equation, you can solve T1. And, okay, any other questions? Okay, so let's go through our summary. So first, just the convention for R3, we write the axis like this. Z, the X comes close to you. So it's the one like closest to you, I would say. And then the Y is a little off to the side, to the right. And your Z just goes up. Okay, just how to remember how to write this. A sphere, well, if we ignore the A, the B, and the C, the sphere in R3 is written as X squared plus Y squared plus Z squared is equal to R squared, which is very similar to the circle in R2. And then the A, the B, and the C are just going to be the center of your circle, and you put a negative in front if you want to go positive A, so it's with center A, B, C. The cylinder is very similar. You just don't restrict the Z-axis. So you have X squared plus Y squared, and you don't restrict the Z-axis. And then that allows the Z to go plus or minus infinity. So the Z has no restriction. Okay, we use the same notation to talk about vectors in R3 as we did in R2. And if you want to find the vector going from P to Q, you just take the square root and then you do again, you subtract the components. The second component, the component of q, a2 minus a1 squared, b2 minus b1 squared, and c2 minus c1 squared, and you take the square root, that's the Pythagorean theorem, and that will give you your length. So if you were just trying to find PQ, that would be the components a2 minus a1, b2 minus b1, and c2 minus c1. And then in order to find the length, you square each component and you take the square root. If you want to find the line going through some point, so in order to determine a line, you need a origin point or a point on the line and a vector parallel to the line. It's very similar to in R2, you need the y-intercept and the slope of the line. So very similar to that. And so what we end up doing is we say our R of t, our line, is going to be the initial point, P0 or R0, plus t, and this t is the parameter of the line. It tells you how far you are on the line, times v. So if here's your line, let me go here. So if here is your x, y, and z axis, and here is your line, you end up looking at a point on the line. So this will be your point P0. You find a vector parallel to the line. So this is the vector v. And you write R of t is equal to P0 plus TV. And as t changes, so for t equal to 0, you're right over here. This is t is equal to 0. For t equal to 1, you're right over here, t equal to 1. For t equal to -1, you would be here, t equal to -1. And so you can write it in terms of the x, y, and z vector components plus the v vector. So here's v and here's P0. Or you can write each component individually, what x is, what y is, and what z is. And just remember that this x is really x of t. So this x changes with t, x of t, y of t, and z of t. If you then want to find the line going through 2 points, you create the vector between them, v, and then you use one of the points p to write R of t is equal to this p plus tv, where v is equal to the vector going from p to q. And that's the end of this section. Any questions? Okay. So let's continue with the next section, which is the dot product. Okay. So I'm going to say this a couple of times, but we will review it a bunch of times. The dot product is supposed to capture what cosine originally does. That's what the dot product is meant to do. And we're going to see another thing. It's called the cross product, and it's supposed to capture what sine did. Okay, but instead of using sine and cosine, it's much more preferred if you're in 3 dimensions or higher dimensions to use the dot product. So first, what is the dot product? If you have a vector v, you have a vector v, which is equal to v1, v2, and v3. And you have a vector w, which is equal to w1, w2, and w3. Then the dot product between them, you take v dot w, is going to be v1 times w1. So you take this component, the first component of the first vector, and you multiply it by the first component of the second vector, plus you add the v2 times w2, so the second component of the first vector times the second component of the second vector, plus v3 w3. So again, third component times third component, and you add them and you get a number in the end. Because if so, you start with 2 vectors. So we can say you start with 2 vectors from R3. So let's say something from R3, and then you put another thing from R3 and you get a number from R. So it takes 2 vectors and it gives you a number. That's what you want to remember. So here is the definition. V is V1, V2, and V3. W is W1, W2, and W3. And when you dot them, you do V1, W1 plus V2, W2 plus V3, W3. So here's an example. Any questions so far? Okay, so here's an example. They want us to find the dot product of 2, 3, 1 dotted with -4, 2, and 5. And this is going to be equal to 2 times -4 plus 3 times 2 plus 1 times 5. So 2 times -4 plus 3 times 2 plus 1 times 5. First components get multiplied, second components get multiplied, third components get multiplied, and you add them all together. Okay, so that's -8 plus 6 plus 5, which is going to give you 3. And you get a number. If you're just in R2, 2 dimensions, so your vectors have 2 components, do the same thing, just only with those components. You don't have a third component. Now, if you want to find the magnitude of a vector, we said that the magnitude is the square root. Let me write V is equal to V1, V2, and V3. So the magnitude of the vector is V1 squared plus V2 squared plus V3 squared. Now, if you dotted this vector, V dotted V, you would get V1 times V1, which is V1 squared, plus V2 times V2, which is V2 squared, plus V3 squared. And that's the same as the, so you don't have a square root here. So that's the same as the magnitude of V squared. So that's what we have here. Dotting V and V dotted with V is the same as its magnitude squared. So that helps you remember. I mean, I prefer to remember it through the Pythagorean theorem, but it's an interesting relationship that we know what the dot product does if you have 2 different vectors. What happens if you take the dot product of the same vector with itself? You get its magnitude squared. Okay. Some important properties of the dot product are it's commutative. So you can flip the dot product. Why is this? So if I take V dotted W, and again, V is equal to V1, V2, and V3, and W is equal to W1, W2, and W3, then V dotted W is equal to V1 W1 plus V2 W2 plus V3 W3. We can switch all of these, so we can say this is the same as W1 V1 plus W2 V2 plus W3 V3, and that gives us W dotted with V. So you can flip them because each component just gets flipped, and that means that they're commutative. Any questions? Okay. So you have commutativity. Very similar proof will show that if you take the scalar times V, you can move the scalar to the other side or just take it out. Again, just take the scalar from each component and you can move it around and do whatever you want with it. It distributes. And I would not say that you need to memorize these rules, because if you ever need to go through if you ever need to do one of these rules, you can just do it by hand. You can open up the dot product and move the stuff around. So you don't actually have to memorize the stuff. And like we said, you have this relation V dotted V is equal to the magnitude of V squared. So they ask us to verify the distributive rule with this U, V, and W. So what is U dotted with v plus w. Well, that's going to be, so let's start by figuring out what v plus w is. V plus w is going to be 1 plus 3, which is 4. 2 minus 2, which is 0. And 2 plus 5, which is 7. So that's our v plus w. And then when you dot it with u over here, you're going to get the force component, so 4 times 4, plus 0 times 3, which is 0, plus 3 times 7. Okay, so that's what you get here. 4 times 4, 3 plus 0, 3 times 7. And that is 37. Okay, so we got one side. What happened? There we go. Instead of doing this, they want us to check that you can distribute it. So you can do each side individually. So what is u dotted with v? So u dot v is going to be equal. So that's here, 4 times 1 plus 2 times 3 plus 2 times 3. 2 times 3. And that is going to give us 16. And then for the other side, what is u time dotted with w? So u dotted with w is 4 times 3 plus 3 times -2 plus 3 times 5. And this gives us 21. So you add them, 16 plus 21, and you get 37. Okay? Questions? So, like I said, the dot product is trying to capture what cosine originally did. And we have a very specific relationship between the dot product and cosine. And that is that v dotted with w is equal to the magnitude of v times the magnitude of w times cosine of theta. And generally, I don't recommend that people memorize stuff. I think it's important to understand things. But in this case, they're like, for the dot product is one thing you should memorize, and that's this. And for the cross product, there's one thing that you should memorize, and we'll talk about that when we get to the cross product. So in other words, so let me rewrite this here. V dotted with w is equal to the magnitude of v times the magnitude of w times cosine of the angle between them. So this is the angle between v and w. Here's your v. Here's your w. Here's theta. So another way we can rewrite this is we can say cosine of the angle between, and we know it's very important to find angles between vectors. So it would be nice if we can have a nice formula to find the angle between vectors. And we can say cosine of the angle between these vectors is equal to v dotted with w over the magnitude of v times the magnitude of w. So we just move this to the other side. And another thing we can then do is say the angle between two vectors is equal to cosine inverse of v dotted with w over the magnitude of v times the magnitude of w. And that will always tell us we want to find, if you're ever asked for the angle between vectors, this is the formula to use. I'm going to skip the proof. So here are the two formulas. cosine of an angle between two vectors, and here are your two vectors, W and V. Doesn't actually matter the orientation. Yeah.
So we should use this, well, only if we use the angle.
So far, this is for knowing the angle between vectors. The dot product will come up in a couple of different instances, but we will keep showing how the reason it's coming up is because you're trying to find the angle between vectors. So that's the intuition. The dot product is to find angle between vectors. And you don't have to play around with cosine. I mean, you write the cosine inverse, but the dot product itself has no cosines in it. It's just multiplying the components of vectors. So it's a very, very simple operation, but it will give you a lot of information. Yeah?
If you have two vectors like this, how do you know if the angle between them is that or like the long way around?
So you always are going to look for the smaller angle. So that's the angle between 0 and pi. Any other questions? Okay. So now they ask us to find the angle between the vector 3, 6, 2. So let me write that. So let's say V is V is equal to 3, 6, 2. And W is equal to 4, 2, 4. 4, 2, 4. So we want to find the angle between them. So the formula is the angle is equal to cosine inverse of V dotted W over the magnitude of V times the magnitude of W. So what is this? So first we would like to find V dotted with W. So V dotted with W is 3 times 4, which is 12, plus 6 times 2, which is 12, plus 2 times 4, which is 8. And this is going to be 20 plus 12, which is 32. So 32. So we can say this is cosine inverse of 32 over, okay, what's the magnitude of V? Well, that's going to be the square root of 9 plus 36 plus 4, which is going to be the square root of 49. And what's the magnitude of W? Magnitude of W is the square root of 16 plus 4 plus 16. And that's the square root of 36. And that would be 7 and 6. So you put that over here. So I don't know what the cosine of this number is. I don't know what the cosine of this cosine inverse of this number is, but if you don't have a calculator, you can leave it like that. So that's what the angle is right over here. This is the angle, some number. And if you have a calculator, you can figure out exactly what this angle is. Take the cos, yeah.
What if like the two vectors are parallel?
So if you do this, you will find that you will get 0. And the reason you're going to get 0 is that you're going to have V dotted with something that has the magnitude of V. Let's just say V dotted with V. So you can get cosine. You can have like a lambda, but you can come out. So cosine inverse of V dotted with V over the magnitude of V times the magnitude of V, which is the magnitude of V squared. Well, we know that these are the same, so you're going to get cosine inverse of 1, which is 0. Any other questions? Okay, so yeah, they did the same thing. You find the magnitude, you get 7 of V. You find the magnitude of W, you get 6. You plug this in, and you get cosine of this is 32 over 42, and that would be 16 over 21. You take the cosine inverse, and they tell you that the angle is 0.705. Okay? So if you take V dotted with W and you end up getting 0, you know that your angles are perpendicular or orthogonal. So this is how, sorry, your angle, your vectors will be here, V, and W is here. And the angle between them is going to be 90 degrees. And so that's a great way. Very often we do want to know whether vectors are perpendicular. And this is a great way to know that. Take their dot product. If their dot product is 0, then you know that they are perpendicular. And the reason for that is if you just again go and you say, I want to find cosine inverse, and now you're going to have 0 on top because you took the dot product, and we said that the dot product, let's imagine that the dot product between these two is 0, right? So you get 0 on top over magnitude of V times the magnitude of W. So that's cosine inverse of 0, and that's pi over 2. Right? Because, yeah.
So it's perpendicular to the pi over 2.
Yes. Yeah. And, right, because cosine of pi over 2, well, cosine represents the x-axis. This is going to be cosine of pi over 2. What's x when your vector has the angle pi over 2? Well, the x dimension is 0, so cosine pi over 2 is 0. So cosine inverse of 0 is pi over 2. So pi over 2 is telling you that you're perpendicular, or the dot product being 0 tells you that you are perpendicular, which is very useful. And if, again, you get that your angle, if you get that you plug it in the formula and you get 0, then you know that they are parallel. Okay. So let's try with I, J, and K, because we know that I, J, and K are perpendicular. So I we know is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. Right? And if you make your axis X, Y, Z, this is your I. This over here is your J. And this over here is your K. And they are perpendicular. So what is I dotted with J? Well, that is 1 times 0 plus 0 times 1 plus 0 times 0, which is 0. Check. Let's just do one more. J dotted with K. 0 times 0 plus 1 times 0 plus 0 times 1 equal to 0. Check. Any questions? Okay. So they try it with, ij and k. So testing for orthogonality, or testing if vectors are perpendicular. So they want us to determine whether V is orthogonal to U or to W. So what is V? V is 2, 6, 1. So V is equal to 2, 6, 1. W, U is equal to 2, negative 1, and 1. 2, negative 1, and 1. Okay, so take a minute. Try to do this. Let me know what you get. Yep. Negative 1. Okay, so they're not perpendicular. You're saying they're not perpendicular. Anyone else? Yep. Yeah. Doesn't look like they're perpendicular, so you get 4. 4 minus 6 plus 1. So yeah, negative 1, not perpendicular. And they got the same thing. Great. Second problem, do the same thing. You get 0, so 2 times negative 4 is negative 8. And then you get 6, so negative 2 plus 2 is 0. So you get 0. Any questions? One other thing that we can do, but will not really appear that much, unless and it won't really appear until vector calculus, which is, way far in the future. So we're not going to focus too much on it, but you can tell if the angle is obtuse or acute by telling if your dot product is negative or positive. And again, that goes back to the formula. And I am going to skip this example, but you're welcome to do it. Again, you take the dot product. If it's negative, you have an obtuse angle. If it's positive, you have an acute angle. So let's see what else. Okay, probably outside of finding an angle, the second most important by far, and I would say that there are two very important uses for the dot product. One of them is finding the angle, and another one is finding the projection of one vector onto another vector, which is very useful. So cosine, in general, is meant to represent let me go to a different thing. Okay. Cosine is meant to represent the projection of a vector onto your x-axis. So if here's a vector, and you want to figure out what is this projection, what is this length right over here? Well, that's your x direction. So if your vector over here has length r, so here's your vector v, and if the magnitude of v is equal to r, then we say that x is equal to r cosine of theta. Give me this angle, And I will tell you what this length over here is. That's this length, which is the length in your x direction. So a very important property of cosine, which we use all the time, is how to project vectors into the x direction. That's in fact why cosine was invented. And sine does the same thing in the y direction. So if you want to find the projection in the y direction, that's here. Then we say y is equal to r sine of theta. Now in 3 dimensions, we would want to do something similar. If here is your vector v, and here is your vector w, we would want to know, and for any 2 vectors, you can think what happens if I project one onto the other. So what happens if I go here and I walk in a straight line to the other vector? What is this length over here? What is that length? And here's the angle between them. So that's a very important thing that we would want to be able to do. And that's right here in this picture. You have a vector v, you have a vector u. We will call the projection of u onto v, u, 2 lines v. People use different notations, project or whatever, but here we're going to do u, 2 lines v. And that means u projected down onto v. So that's this over here. That's u projected onto v is right over here. Now we know that u projected onto v is the same as the magnitude of u, that's r, times cosine of theta. Now this gives you the length. This gives you this length right here, the length of this vector. If you then want to find the actual vector, you will multiply that by the unit vector of v. So that is, this is the length right here. Give me a second. Here's our length. And you multiply that by EV, the unit vector of v. So we can imagine taking v, finding its unit vector. That's right here, EV. Then multiplying it by this length, which again is just u cosine of the angle, because we know that the projection, we know that the projection, we can imagine that this over here is our v, the x-axis is our v, and this over here is our u. Okay, I don't want to confuse things too much. Let's just keep it this way. But we know that if you're projecting this vector onto this vector, you look, in order to find the length, which is this length over here, you look at the magnitude of your original vector, which we said was r. So x is equal to the magnitude of the original vector, which is magnitude of v, times cosine of theta. So that's right here, magnitude of u times cosine theta. But in order to find the actual vector, you just multiply by the unit vector of v. Okay, but this is the same as the magnitude of u times cosine theta. And then the unit vector we know is v over the magnitude of v. Now we can add another v squared to the bottom and cancel it by adding a magnitude of v on top. So that was this step. We can do that. And we know that if you look at this v over here, we know that if we ignore it, and that's this v over here, the magnitude of u times the magnitude of v times cosine of an angle over the magnitude of v squared is equal to the dot product between u and v. So that comes about from taking, so what's the dot product of u and v? So the dot product u dotted with v is the magnitude of u times the magnitude of v times cosine of theta. So if I take this part, magnitude of u times magnitude of v times cosine of theta, I get this u dot v. And then the bottom part, we know that if I take a magnitude, if I square it, I get v dot v. So you just put that on the bottom, divided by v dot v times v. So now we know that our projection in the v direction is very simply u dotted with v over v dotted with v times v. This is our projection. Yes.
What does it mean to project the vector onto another vector?
So when we're projecting a vector onto another vector, we can imagine having v here and having u here. So here's our u and here's our v. And we would first want to find, if I go from here and I go in a straight line to the other vector. So you can imagine this is a vector and here's another vector. For any one, I can go, I want to go from here right to here. And I want to first find this length. So that would be this length over here. Well, that length is going to be the magnitude of u times cosine of theta, where theta is the angle between these two vectors. Okay? So that's the magnitude between these. And if you just write down the formula step by step, you will get to the projection of u onto v is u dotted with v over v dotted with v times v. That's the formula for the projection.
Also, what does the E sub V represent?
The unit vector in the direction of v. Any questions? I'll review this again. We'll do examples. But again, there are two important parts of the dot product, the angle and projections.
So I understand like projection. I understand like what you're doing and stuff. Like
I just want, have a nice weekend, everyone. And yeah. You want this vector, it goes in the direction of v. So it's pointing in the direction of v, but it has the length of this projection. So it's basically, imagine taking this vector u and squishing it down onto here. And we will go through a lot of examples. Yes. Okay, perfect. Any-
Okay. And then also, oh, okay. Yeah. And then,
Let me,
is your name Israeli?
Yes, yes.
Yes, I figured my mom's name's Galit.
Is what?
Galit.
Delete, yeah.
I figured.
Israeli.